And do you still see my face off to the side in a little screen?
Yes, I do.
Yes. Okay. Okay, wonderful. So now you see the big sheet also, and there's something so anyway, let's just quickly. Oh, and let me start the stopwatch too. And there. Okay. Last time we were discussing, now we're after this these the last two lectures and the next couple lectures all fit under this microscopic theory of refractive index uh, you know topic. I mean, that's the overall sort of theme: microscopic theory of refractive index. And you know, that's for the microscopic picture, we introduced the Lorentz model. All right. And I just wanted to make clear what the connection, like why we care about the microscope, why we care about the refractive index, you know. And so one thing I wanted to do quickly was, um, let's say that um, this was the wave equation in the medium that we derived, right? And I just wanted to remind you, and I started to remind you about the vacuum right there. And then there was something else I wanted to tell you, and to make the connection with the refractive index. I started to make that connection right here, you see. Uh, so here's the vacuum part, and then there was the medium, and there's the refractive index. And there was something I wanted to say in this connection. Um, so in the vacuum, because the refractive index, I just want to say something more right now before we begin. So let me start the lecture for today, and this is 0430 21. And so we are developing a theory, a microscopic theory of refractive index. And um, and I want to sort of give you a sneak prep, like a heads up, I guess is the only way to say this. Heads up that for a medium, the refractive index n is a complex number. So when that happens, I don't want you to suddenly, reel from shock. It's a complex number. And so basically what's going to happen is we'll see that the refractive index, and I've discussed this before, that there's a real and an imaginary part, and the real part is just the usual bending at the surface, and this imaginary part actually has to do with absorption and scattering. And of course, the sum of the two is attenuation. In the context of the laser, because we're looking at near resonance things, the absorption tends to sort of dominate. Okay, dominates for lasers, and we've discussed this, we've touched upon this before. All right. Now, the reason I wanted to bring this up today is that we will deal with this later. So, um, uh, so the heads up, there's the heads up, but I just want to remind you, so reminder, that in the case of the vacuum, our wave equation up top uh, just said minus 1 over c squared. right? The mu naught, and there was an epsilon naught that came out, and so then you got this. And in this case, the simplest. So here's the stuff I wanted to tell you about. The simplest solution to the wave equation is the plane wave. There are other solutions, but the plane wave is the simplest solution. And what is that solution? That the electric field, it turns out, I mean, a double derivative in space must equal 1 over c squared, a double derivative in time. So who is the guy who's going to, like, what kind of function is that? And well, it turns out that, it is the plane wave. So let me just, all right. So there's an amplitude, there's a vector sign, that's just the polarization. And here's the part I wanted to focus on, that, if it's moving in the z direction, right, then it's kz minus omega t, right? That's a monochromatic plane wave, and that's the simplest solution, okay? So traveling in z direction, okay? So there you go. And of course, when you take the double derivative with respect to space, right, the left hand there, this part, then what are you going to get? You're going to get the ik is going to come out twice from each derivative, and then you're just going to get back the original function, right? And this is equal to 1 over c squared, the double time derivative, right? And each time you take the time derivative, there's a minus, and there's a minus sign, and then the I omega is going to come out on each derivative. So if I plonk the solution back into the wave equation, that's what I get. And this, of course, leads me to the well-known relation that k equals omega over c, right? This is what you expected. And that's where it comes from. All right. Now, in the medium, okay, so this was for vacuum, all right? In the medium, what happens is that this k, instead of just being omega over c, it becomes omega over c divided by n, right? There's the refractive index. And so this becomes a n omega over c, all right? And so the thing I was leading up to is that in the past, I've just given you Beer's law as a statement, without any justification, all right? So, but today, you remember Beer's law, right? Beer's law was that there's some medium, right? And let's say z starts from here, z equals 0, and then z goes in that direction. And let's say you have a wave coming in, and it's I naught at z, and then what's the intensity at this point at some detector, right? And so Beer's law, remember that? Beer's law, we said, is that the intensity at z is the incident intensity, and then there's this exponential attenuation, right? And this was the attenuation coefficient, z. And it could also be the absorption coefficient if absorption is what's dominating. So this was Beer's law, all right? And what we're going to see is that this absorption or attenuation coefficient is constant, is linked to the refractive index, all right? And so we'll see that in just a sec. So the refractive index is n times omega over c, but the n is real and it has an imaginary part. Okay, and so when you take this complex form of k into the solution, all right, so complex k now goes into the wave, the plane wave solution. Okay, and what do you have? You have now the plane wave So there's a E naught, there's a e to the I, right? And k is, now there is a nr plus I ni z, right? And then minus I omega t. And so now you see that there is, what does the imaginary part of the refractive index do? Well, it gives you, so you can separate this out into a normal I n sub r, and there, sorry, I forgot something here. K was, I forgot the omega over c part. Let me just put that in. Omega over c. So I have a n sub r omega over c z minus omega t, right? And the e to the I times the I, you see it gives me a e to the minus n sub I omega over c z. So there's this exponentially attenuating part, and there's the usual propagating part, right? So, I mean, basically, this is the real part of the k vector and z. So this looks like, this looks like e to the I, and if I write this as k sub r, z minus omega t. So that just looks like a propagating wave here. So this is the part that's propagating wave, but then I also have this exponentially dying off part, because the two i's, this I and this I and this I combined. So I have an exponentially, so this is the exponentially attenuating. Okay, so I have an exponentially attenuating propagating wave. And the intensity, of course, is given by the absolute value squared. It's proportional to the absolute value squared of the amplitude. So when you absolute value square this, you see right away that there will be a, this comes from the E naught squared. There's the intensity in the beginning. The e to the I, well, when you take absolute value squared, it goes away, but you're left with the other one. So this y, when you square it, it becomes a minus 2 ni omega over cz. And of course, this, if you compare with the Beer's law, right, that was I naught e to the minus attenuation times z. So you can see that this A that we had defined earlier, okay, what was this? This was the attenuation constant. And for lasers, this is the absorption, right? Well, this is just equal to the refractive index. It's actually 2 times the imaginary part of the refractive index times omega over c. Okay, so that's this is your absorption. Okay. So I wanted us to have this result in mind, that when we look at the refractive index, the imaginary part is directly related to the absorption, right? Okay, well, so knowing this, now we can, so that's why, that's why we're interested in the microscopic theory of the refractive index, because first of all, we will be able to relate it to the attenuation and the absorption. And also it turns out the real part is also interesting, because it tells us about how fast this wave is propagating through the medium. Okay, because it's related to the phase velocity and group velocity and things like that. So anyway, let's go back now to okay. Uh, so you know the so the refractive index, real and imaginary parts, is important. Okay, and now back to the Lorentz model. That's where we were, and we are on the brink of discovering for the first time a microscopic theory for the refractive index. And how far had we made it till? Let's see. So what we had done was that we had written out the Lorentz equation, okay, in the model, in the Lorentz model, an equation for the oscillating electron. All the quantities here are things that we believe in, that actually exist. That's the natural resonance frequency of the electron, okay. So that's important, omega naught is the natural, did I say resonance? Well, natural frequency is what I meant to say. Natural frequency of the electron, okay. That's the frequency at which if you zap the electron with some driving pulse, and you zap it and let it go, then once zapped, it will kind of ring back and forth, okay, at a frequency which is very characteristic for the electron of that element. So for rubidium, the electron might oscillate back and forth at a certain frequency, which is different from cesium or sodium or some other element. All right, so that's a natural frequency for the electron. And then, of course, electron charge, mass, this is the driving field. Okay, and this thing here is the displacement of electron from the equilibrium position. Okay, which is assumed to be the origin. All right, so now we just have to solve this. Okay, so solve the Lorentz model equation. And what's going to happen? Like, what are we going to find? So, I'm sure we'll be able to solve it, but what's that going to give us? So the roadmap for us is, so we have to solve this equation, right? And so let me just write it out once more, just so that it's on this page. Okay, so remove that. And we're going to solve this, and when you solve, what you're going to find is that you will find the solution will be x, right? You'll find something. Now remember, this is the displacement away from the origin or from the equilibrium position. So if I multiply this, now that's the displacement. If I multiply this by the electron charge E, then what you get is the induced dipole moment. Okay, remember what was the induced dipole moment for each atom? It was lowercase p from our previous, like when we were talking about the electric polarization. All right, and now if I multiply this by, so if I multiply this by the, so if I have this little p and I multiply it by the number density of the atoms, of the material, then I will get the induced dipole moment per unit volume. But that, of course, is just big P. Okay? And this big P, so now, and then what's the next step? So I'm just trying to tell you all this. So that's the first thing, that's the next thing. And now this P that I find, I also had another relation, another place where this appeared. Okay? And because the electric polarization is something that I know macroscopically also, and so it has to satisfy this equation as well. Remember, so because this D is all this, so once I have this guy, then this P, and this is a microscopic, like P from the microscopic theory, okay, must satisfy the Maxwell's equation, which is this guy. Must satisfy this equation. Where this displacement field is epsilon naught E plus P. Okay, so when I make this connection, then I will be able to find, by plonking the P determined from the microscopic theory into this equation, into the wave equation, I will be then, just as I did here, just as I found this relation, k equals omega over c, from the wave equation, right? I should be able to then find the new relation, okay? I should be able to find k equals omega over c times something, okay? And we know that this something is the refractive index, right? It's n times omega over c. I just sort of postulated that here. Yeah. I just said, this was kind of a postulate. I just said that the speed of light is going to change because it's going to be c over n, and so you'll get this. But now I'm actually going to derive this relation, okay, and so I'm going to see something here. And that is my refractive index, and this will lead to the first time we'd have a microscopic expression. By that I mean involving, atomic polarizability and things like that. I have a microscopic expression for n. And remember, the whole reason why Lorentz, maybe I don't know if I emphasized this appropriately last time, but the biggest advantage of the Lorentz model is that for the first time, because it assigned a spring-like interaction, for the first time you will have resonance. The concept that there is a natural frequency omega naught, and then there is a driving frequency from the electric field. And so now you can have resonance, because it's the first time And so this is a good thing to write down here, that, what is this advantage of a microscopic for expression for n? What it means is that for the first time we will have, and I just want to be, don't want to miss the chance to be all Van Gogh here. Where's my black? I keep misplacing my black pen. I don't know where it is. But for the first time, we will have a microscopic expression for n, meaning really it is the first time. I watched that. Sorry, just a little bit anal about it. First time we'd have a resonance physics understanding of refractive index. Okay, and that's how we'll understand why things have colors, and why if you don't do the Lorentz model, then you don't ever bring in resonance, and so everything is just okay, yeah, so things you put in white light, it spreads into the colors, and that's about all you can do with it, right? It's all the interesting stuff all happens near resonance. I mean, that's how lasers can be built, and 90% of all interesting stuff in light atom interaction happens on resonance. Okay, otherwise we'd still be doing optics from 300 years ago. So that's the roadmap that we're going to follow here. Okay, so anyway, let's jump to it. The solutions themselves are pretty straightforward. All right, so let's just do it. Are we good so far? All those who say we're good, say aye.
Aye.
Whoa, okay, several ayes. Any nays? Oh man, we're not a democracy at all. I can tell you that right now. It's a total dictatorship. Like, I mean, I feel like Putin all the time. All right, well, I will continue. Okay, so let's see. This is going to be an easy one to solve. Here's the equation, and you look at it, and you realize that, let's see, so, the thing is that if there were no driving field, right? So I'm going to solve it now. Solution. Okay, so the first thing is that if no driving field, then this would have been trivial. Right? So if no driving field, then you would have just said, oh, well, then I have this trivial equation to solve, right? And so you would have said, oh, well, then the solution is simply some constant, and e to the minus omega naught t, right? Plus or minus, whatever, but you get the idea. So this would have been the solution, something oscillating at omega naught. Now, when you do have a driving field, for a driving field at frequency omega, what happens is that, and so just think of yourself pushing a child on a swing, and if you were to push the child and then stand aside, and then the child and the swing oscillate at a certain frequency, but if you were to grab the swing and the child and push it back and forth you can push it back and forth at whatever frequency you like, right? And maybe in the beginning, it takes a little while, like maybe if the child is a really heavy, think of a child pushing his dad, right? And so in the beginning, maybe the child struggles because the dad's kind of a heavy object. But after one or two swings, then the child kind of asserts his, and so now it's the driving frequency at which the system will oscillate back and forth. So you expect now that the solution is going to be, there will be an oscillation at the driving frequency now, and sometimes you say in the long time limit, I mean the driving frequency is going to win out, and so you expect that, right? Um, and um, and then of course there's the other part of this, which is still, let's call it A, and and that's what we expect. So the thing is that why not just try this solution, okay, in the original equation, and let's just see what form this has. All right. So we can try this. Now, of course, the driving field at omega, this looks like E naught, right? There's a E naught, and it's a vector E naught. And what is the vector E naught? It's just the amplitude times the polarization. So let's, there, that's the polarization. Okay, this, and it's a plane wave, let's say. So it would be e to the I kz minus omega t. But remember, this we threw away because we said that the long wavelength approximation, we've discussed that already. So this looks like a polarization E naught e to the minus I omega t, right? And that's the omega t, that's what we're saying, the driving frequency. And then this is the response of the atom, all right? So let's just assume this sort of solution, okay? So let's plonk this expected solution into the Lorentz model equation and find A. Okay, so let's do it. So the double derivative with respect to x, with respect to time, right? That's the left-hand side. So I'm just plonking it back in there. So the double derivative is minus I omega squared, and then I get x back. So that's a e to the minus I omega t equals, on the right-hand side, I have a E over m. And the electric field I just wrote out here is a polarization E naught e to the minus I omega t minus omega naught squared, and then x, right? And x we said is a e to the minus I omega t, right? So I just plonked it right back in, and you notice that these exponentials go away. Something interesting does come out from this, meaning the resonance thing. So I solve for A, right? So that means I collect the A terms. You notice that this guy here, the minus squared goes away. The I squared gives you a minus omega squared, right? So if I solve for A now, then here's the term that does not have any A in it, and so you get that. And then the A terms, when you collect them over, this comes over to the left-hand side, gives you a positive omega naught squared, and you still have this. And now you see something very interesting, okay? So that's your A, and so that means your solution, okay, is A times this was the solution, right? This was the solution we were saying that we would expect. We've solved for A, so now I just need to put in the e to the minus I omega t, and there. Okay, so here's the solution. Okay, and if you multiply both sides with e, as we said here, you actually have your, we can even write that down. We have the induced dipole moment. Okay, so the induced dipole moment is just E times that. So you have E squared over M. And this, well, okay, so I can, there. And if you multiply that with a M, then you also have your polarization, right? So there you go. All the things are there, all right? And one of the things that you notice right off the bat is that look how beautifully resonance came into the picture. So meaning that, you know, resonance, that if the child happens to push the swing at the frequency that the dad and the swing system like to oscillate at. So I mean, if the driving frequency happens to equal the natural frequency at which the electron likes to oscillate, then A, the amplitude of the oscillation, right? This guy, it actually blows up, right? So becomes very large. In fact, here in this model right now, it's actually blowing up, going to infinity. And so that's a little unphysical, but it definitely does become very large. All right. So that's something that wasn't there in the previous things that we've done with the refractive index. And so now let's take this idea and see what it gives for the refractive index now. All right, and then we will at that point take a break. We're close, so let's just do that. So now what we'll do is substitute the polarization is equal to the number of dipoles per unit volume, E squared over M, the polarization of the driving field, amplitude of driving field, there. Okay, in the wave equation. Okay, and of course this D is epsilon naught E plus P. All right, so what you're going to get. So let's just yeah, I guess so let's just do it. And okay. just one sec. I'm there. Just one sec. So the double derivative with respect to space, with respect to time, and then okay. Okay. Yeah, that's good. All right. So yeah, let's just do this calculation now. So the double derivative with respect to the electric field. Now, what is the electric field? Just to remind you, the electric field, the driving field was E naught. There was this polarization, e to the I k z minus omega t, right? Um, and so okay, so now there is one thing I did want to bring to your attention, um, that you see now I'm keeping the kz, okay, because there is a double derivative with respect to space coming up, and the reason is that previously when we were talking about a single atom, then the variation within the atom, there is no spatial variation of the electric field within the extent of the atom. And that's why we threw that away. But now that we're talking about the macroscopic polarization, so we're talking about atoms that are located at different z's. And of course, yes, I mean, at any one atom, the spatial variation of the electric field inside that atom is still negligible. It's uniform within the extent of the atom, but the atom's locations are different, right? I mean, so there is a z dependence where things are at, and so that's why now we keep that. And also, I mean, this is the double derivative of the electric field. So I mean, the electric field, uh, because the sample has a z, has an extent over z. So the electric field is different at different z locations. At any location, if it sees an atom, then within that atom, the electric field does not vary spatially, but it has different z locations. So when you take the double derivative with respect to space, you get the ik squared, right? And then the original electric field minus mu naught, and there is a double derivative with respect to the epsilon naught e, right? Let's do that one first. So mu naught and epsilon naught, and there's a double derivative with respect to time of the electric field, and you see that you get a minus I omega squared, right? And then back with the e, okay? And then you have a minus mu naught double derivative with respect to time of the polarization, okay? Now the polarization is given right there, okay? So double derivative with respect to time, well, you get the minus I omega squared, okay? And then the whole thing repeated again. Well, and let's write down the constant. So there's a m, there's a e squared over m, there's the omega naught squared minus omega squared, and then you just get this polarization E naught e to the minus I omega t again, right? Which is just the electric field again. And just remember that, this is the polarization, this was the polarization at the location of the single atom, which means that the polarization at some location z would be all of this times the polarization E naught e to the I k z minus omega t, right? Because I hope that I didn't confuse you on this point. Like, I mean, this is the polarization at atom located at the origin. That's, that was the Lorentz model that we did. Now, there are many Lorentz oscillators located at different z locations, and so the polarization anywhere is given by, you have to insert the e to the I k z back in for that purpose. Okay, so this is a m e squared over m divided by omega naught squared minus omega. Okay, so this is, for a sample spread across z. Okay, and this was for an atom located at the origin. All right, so now I substituted this guy into the wave equation here. Okay, and I get this. What you notice is that the E cancels everywhere. Okay, the mu naught epsilon naught, let's replace that with a 1 over c squared, and the mu naught, let's replace that with a 1 over epsilon naught c squared. Okay, so I'm just using I'm using mu naught epsilon naught equals 1 over c squared, right? So I did that. And so now what do I have? I have k squared from here, so it's actually a minus k squared because of the I. And then I have minus 1 over c squared. Minus squared is plus, I squared is minus omega squared. Okay, equals, oh sorry, not equals, but by the way, all of this was equal to 0, right? Because we substituted that in the wave equation. This, and then from here, what do I have? I have a minus 1 over epsilon naught c squared. The minus squared gives me a 1 I squared, so that's another minus squared omega, minus omega squared, I mean. And then I have a m e squared over m. All of this is 0. Okay, and so let me now simplify this. Let's take the k squared over to the right hand side. All right, so there, what am I left with? You'll notice that I'm seeing the, this is a plus omega squared over c squared, and here I have a plus again omega squared over c squared. There's the epsilon naught is left. So I have a n e squared over m epsilon naught, right? This epsilon naught, divided by omega naught squared minus omega. Okay, so what I see is, so therefore k squared equals omega squared over c squared. That's factor is common. 1 plus n e squared over m epsilon naught divided by omega naught squared. There. And so, taking the square root, this is omega over c square root 1 plus m e squared over m epsilon naught 1 over omega naught squared. Now this is the final expression that I get, and let us compare it to, for the medium. Remember, I was saying that we expect a relation like this, right? K equals n omega over c, where n is the refractive index. So if I compare this with K equals n omega over c, then what this is telling me is that the refractive index n, and now this is the first time that I have from a microscopic theory, it's the square root. That's the refractive index. Okay, so there it is. And so now for the first time, we have a microscopic origin for the refractive index. Okay, so this is the microscopic origin of and it's written in terms of like atomic stuff, like the natural frequency for the electron, and then the charge of the electron, mass of the electron. So it's the first time we have such a relationship. Okay, wow, I've been talking for like almost an hour today. 51 minutes. That's more than anyone I know can handle. So I won't be surprised if everyone's just kind of fallen off their chairs at this point. But hopefully, the one point that was sort of a bit of a subtle point was when I went from the single oscillator, the polarizability for the single. Just for correctness, what I should say here is that this is the jump that I made here was not quite kosher. Like this was good. Okay, so this is good. That's the induced dipole moment for the one atom. Okay, and this is a good thing. But then when I say that, and so I feel, if you will please hang with me, I feel compelled to make this one point, which I will insert in as another page here, that everything was good up till this point, and then I just made a hasty rush over to, what I should have said is that, this little p here is the induced dipole moment in an atom, and the atom is, the Lorentz oscillator, located at the origin. Okay, if atom is located at Z, the induced dipole moment is P as a function of Z is equal to E squared over N E naught e to the I kz minus omega t, because that's what the driving field is there. Okay, and then from here I could have just said that therefore for n atoms per unit volume, I could have just said that the electric polarization is the number of dipoles per unit volume times E of z. And this is a function of z also. The macroscopic electric polarization is okay, and then everything is okay. Like from here on, that's fine. Okay, so apologies for that, but I think we've fixed it in real time, even though real time has been painful, I bet, for everyone listening to me go on and on here. But it's a bit of a captive audience, and 2.5. It's a captive virtual audience, which is a virtually captive audience. You've had freedom also to fortify yourself with your beverage of choice if the going got tough. So anyway, I'm just gonna stop the recording